So we're going to go through chapter 3, which is the measures of central tendency. We'll talk about what they're used for, what their purpose is, which measure is the best under certain circumstances, and we'll also talk about how you can describe distributions. So all this is going to be useful information to be able to respond to your labs as well as the exam that you will have upcoming. So first and foremost, let's just introduce what the measures of central tendency are. So these are statistical values that basically define the center of a distribution. And what I mean by distribution is a group of numbers and how they fall. Basically, the high scores, low scores, in the middle scores. So what we want to do is find a score that best represents that distribution or that group of scores. So there's 3 measures of central tendency, and it could be all of these that is reported, or it could be one in particular. And there's usually one that's the best depending upon certain scenarios. So let's go through these and talk about the information that you need to know to succeed in labs and homework and your exam specifically. So the mean is the most common measure of central tendency. So mean is basically the average that represents a group of scores, and it's kind of what we call a balance point. So what it is it balances the distribution to where it's more about how heavy the distribution is. So what it does is it balances it to where the same weight is on this side as on this side, but it doesn't matter how many values are on one side. Some values might be heavier than the others. So it is the most common reported measure of central tendency, and you need to be aware that there are 2 different notations for the mean. Again, you will be asked to report the measures of central tendency, and you're going to need to report their notations. So if you're reporting a population mean, instead of saying the population mean, you're going to say the mean for the data set of whatever scores they are is, and the mu, which as you'll notice, let me get red here, this is a mu, it's a Greek symbol, is going to be telling us that you're looking at a population mean. So it should be reported mu equals, and then your number rounded to 2 decimals. And so if you'll notice, to obtain the mean, it's the sum of x divided by capital N. Again, the capital N tells us that's a population size, is what that is the number of observations made within a population. And if you're reporting a sample mean, it's a capital M. And if you'll notice in the equation, it uses a lowercase n because that describes a sample size rather than the population size. It's a sample size. So it's very important that you are using the correct notations, and it's always within a sentence. So if I'm looking at a sample of, let's say like in this little joke here, reading scores, a sample of, or I have the average reading scores were shown to be capital M equals, and then maybe 50.75. So the notation is used, followed by the value that is calculated rounded to 2 decimals. So it's just a way of explaining when you use that capital M that you're talking about a sample very specifically. It's important to know. So when we compute the mean, that sum of x, there's a couple of different ways you can obtain the sum of x. So in this case, we have times, like participants walk through a scary part of the campus, okay? And so the times that they walked in seconds is 8, 9, 5, 5, 5, 1, 6, and 8. So these are just raw scores. So if you see, we can see there were 8 raw scores, right? 8. Oops, that's really scribbly. So, 1, 2, 3, 4, 5, 6, 7, 8 different scores. So that's our sample size or population size. It depends upon whether we're dealing with a population or a sample. In this case, I'm not specifying, I'm just wanting you to see the process. So to obtain the sum of x so that we can calculate our mean, we're just going to add up those scores, which we would get 56. So then we'd plug that 56 into the numerator and divide it by the number of scores total, and then we would end up with 7. So that would be our population mean, which is mu equals 7, or if it's a sample, m equals 7. And since how there's no decimals, it's perfectly fine to keep it as a whole number. That is perfectly fine. So let's look at using a frequency distribution table, though, to compute the mean. So if you notice, I have here these quiz scores, 10, 9, 8, 7, and 6. So it's not a complete frequency distribution table, it's just a glimpse. So a lot of students make the mistake of counting the rows. So you'd have 1, 2, 3, 4, 5. But that's not how many scores there are, because one person scored 10, 2 people scored 9, 4 people scored 8, 0 people scored 7. So we have to account for how many people scored each. So to get our sample size, we're just going to add up this frequency column. And so if you'll notice, our sample size is 8. And so specifically, this is a sample because I'm using a lowercase n to explain that. So the next thing we need to do, because to get our mean, we need to get, that the sum of x, but we have to account for how many of each there are. So what I do is I multiply across. So if you'll notice this column here, I have f times x. So because 10 was only scored once, if we added up all the people that scored 10, it's only 10. But 2 people scored 9. If you added up 9 2 times, it would be 18, et cetera, et cetera. And again, 7, no one scored 7. It's there, but no one scored it, so that sum of x would be 0. You add all these up, and your sum of x is 66. So then you can just proceed at that point with calculating your mean. So that sum of x over sample size, which is 66 divided by 8, equals 8.25. So that would be the mean of these numbers. And that makes much more sense because if you look, right in the middle is 8, that quiz score specifically. So you want to be really careful when you're deciding whether there's a frequency table or not. This is a frequency table because you have this column, x, and then there's this second column with the lowercase f. That makes it a frequency table. Otherwise, if you just have like a label of quiz scores and you don't have a column of possible scores and your frequency column, then it's just raw scores and you just calculate normally. So we can also use what is called a weighted mean. So that's when we take 2 sets of scores and combine them. Well, you can't just always go this mean plus this mean divided by 2 and get the average. You can if they're equal sample sizes, but you can't do that if one sample size is larger than the other, or if they're different sample sizes. So if you have a sample, like it says here, sample A has 20 scores and sample B has 35 scores, it's important to note how many scores there are, those sample sizes, because sample B is going to influence the mean more than sample A because there's more scores. So we have to be really careful to account for that. So I'll show you what this looks like. So I always say 3 steps. Determine the combined sum of all scores, determine the combined number of scores, and then divide the sum of scores by the total number of scores. So that's acceptable if you have raw data set. But if you're given a sample size and means, you're going to use the second way where it says or. And I'll circle this. So this is basically, you're doing the same thing. It's just now you have a mean. And if you calculate the mean, the answer, times the sample size for that mean, you're going to end up with your sum of x. So it's just a backwards way of doing it. But typically you'll see data where it's raw data. And so for each group sum of x, they're added together, and there can be more than 2. And then that total divided by the sample sizes added together in the denominator. So one good way is in your calculator to put parentheses around the sum of x total adding together in the numerator, and then a parentheses around the sample sizes in the denominator that are being added together so that you have appropriate results. So here's kind of an example. So we have quiz scores from a 9 a.m. class and quiz scores at an 11 a.m. class. If you'll notice, here's the scores in the first column for the 9 a.m. class, the possible scores, and same ones in the 11 a.m. class. But then we have the frequency column. So the frequencies is where it's a real big clue that these are frequency distribution tables. And so you have to calculate them separately. So first we want to multiply across so that we can get the sum of the f times x's, so that we can see what the sum of x's would be totaled as for each of these. But then we also want to look at sample size for each. So to get the sample size, we need to add up these frequency columns. So I'll show you what that would look like. So here we have, I have it a population n here and a sample n. They should both be samples. I think is what happened is PowerPoint auto-corrected and made this a capital. Just ignore that and think of it as a sample, because there's 2 different samples. And we added those up, so there was 11 people in this 9 a.m. sample, and there was 14 people in the 11 a.m. sample. And if you add these up, notice the first sample is 36, the second sample is 38. So then we can just plug it in. So we have 36 plus 38 in that numerator, and that's where I would usually put parentheses if you're putting it in your calculator like this. Divided by, and again parentheses, 11 plus 14. So our weighted mean is 2.96. And I accept for weighted mean just a capital M. That's perfectly fine. You don't have to have the subtext of W. So capital M equals 2.96 would be the appropriate way to report a weighted mean for these 2 samples combined. So the next measure of central tendency is the median. Now the median is just the midpoint. And so that is just if scores are listed from smallest to largest, it splits them in half. So the same amount of scores are on the right-hand side as there is in the amount of scores on the left-hand side. So it doesn't take into effect the values. It takes into effect just the number of scores there is. So it divides it into 2 groups of equal size is what the median does. And then you find the middle number within the 2. So to get the median, there's some steps. Okay, there's lots of ways of doing it. You can Obviously, you can plug it into Excel, but if you are provided an example where you have to hand calculate, the best thing you want to do is find how many scores you would have to count to get to the middle. So to get to that middle position for how many scores, you would take the sample size plus 1 and then divide by 2. That plus 1 accounts for the upper and lower real boundaries of the entire data set. So then you have to find, once you get that median position, that's how many numbers you count over. And so it's going to differ between odd and even number sets as far as how you get your actual median. So you're going to want your scores in a numerical order. So let's look at this group here. So for this median, so this is easy because this is an odd amount of numbers. We have a sample size of 5. So to find the position, not the actual median, we're going to count 3 places over, because 5 plus 1 is 6, divided by 2 is 3. So that basically means once we have these in order, either way, if we count 1, 2, 3 over, or 1, 2, 3 over from the other direction, we should be hitting the exact same number. In this case, it's 44. One of the big mistakes I see students make is they do this equation, this portion of it, and they give me this as the result. But that doesn't make sense. 3 doesn't make sense because 3 is well outside of this range of numbers. So 3 isn't the actual median, that's just how many positions you have to count over. It's a little different when the median or when the sample size is an even amount of numbers. So if you look here, this has 4 numbers. So we dropped off one of the numbers. So we're going to use the same process. So 4 plus 1 is 5, divided by 2 is 2.5, which basically means the median is going to be exactly in between 2 scores. So if you notice, right in the middle, it's these 2 scores, 66 and 44. So the median position, if you go 1, 2, if 0.5, it falls right in the middle of these 2 scores, 2.5. So what we want to do is add those 2 scores together and then divide by 2 to get the number that is located right in the middle of those. So the median in this case would be 55. So it's just a way that you can specifically find that median in an odd or an even amount of sample size. So the numbers would have to be listed, highest to lowest or lowest to highest, one or the other, and accounting for repetitive numbers as well. So here's where we can kind of start looking at, okay, when would we report the mean and when would we report the median? Well, think about this small data set. So we have 3 people scored 2, okay, 2 people scored 3, and then all of a sudden out here, 1 person scored 12. This would be considered an outlier. So if we were to calculate the average or the mean would be 4. Well, that really is not very representative because no one scored 4. So in actuality, the mean would not be the best measure of central tendency to describe this data, but the median would, because what the median does is it splits our data in half. So we have 3 people on this side and then 3 people here. So right down the middle, the score of 2.5 is the median, which is the best measure of central tendency. That's where the data peaks. So this is where, like you might think of in the real world, when we talk about annual income. If I was to tell you the average annual income of a citizen of the United States, if I told you the average, it would be well over $100,000 a year. but that's really not very representative of the majority of Americans. The reason is there's some outliers. There's some people that make so much money that they're pulling the mean over. So the best way to describe the United States income is to use the median, and it's somewhere in the 50,000s, the median income of an American citizen. So that's much more representative than over 100,000 as far as describing the data. So the median is the best representation. These are things you want to be able to distinguish between. So the last and probably most rudimentary measure of central tendency is the mode. And that's just basic like grammar school types of things. It's just the most frequent occurring score. So is what you do is you list the scores in order and just find out which score it occurs the most. In this case, you'll notice the score 4 scored the most often. So 1, 2, 3, 4, 5, 6, 7, 8 times is what 4 was represented as. So in this case, mode equals 4. Now, again, mode does not have a notation, so you would just spell out mode equals 4, and same with median. Median does not have a notation, it's just spell the word out equals median. So just to kind of reiterate the notations, there are occasions that there are no notations, and so you could just write the word out. Or there's not consistent notations. Some people have notations, but they're not consistent notations for research in the behavioral sciences. So the mode is very, very rudimentary, and we don't use mode very often in social behavioral research when we're talking about a measure of central tendency, unless there are certain occasions would be used, and I'll talk to you about those occasions. So here is an occasion where the mode would maybe be a good measure of central tendency to report, is if we had a symmetrical distribution, but it was bimodal. So you have these two modes. So if you'll notice, there's 2 peaks in this distribution. And this is basically, they would have to be like exactly 2 peaks, a perfectly symmetrical distribution that's bimodal. So that's when you would probably present your mean, but then you would clarify that it's a bimodal distribution with modes of such and such and such and such. That is the only time that you'd really use a mode for a frequency distribution of continuous data. So with symmetrical distributions, as you can see, this one here on the left-hand side, it's got 1 peak, and basically that peak is right in the middle. If you folded it in half, they would basically be mirror images of itself with the peak, half of the peak on one side, half of the peak of the other. And then the bimodal on the left side that I talked about, you have 2 peaks, but if you fold it in half, they should be mirror images. Then you have what's called skewed distributions. So this might seem contradictive as far as positive skew and negative skew, but always think of where's the majority of the tail at, and where's the majority of the data at, the bulk of the data. So on this one, the majority of the data is on the low end, which would be the negative end, and the tail is pointing towards the high end, which is the positive end. So it's really what we're saying is this data set is skewed away from the positive numbers. It's skewed away from the high numbers. And exactly the opposite with the negative skew. The tail is on the left end, pointing towards the low end or towards the negative side of the axis, with the bulk of the data on the right-hand side, suggesting that the data is skewed towards the high numbers and skewed away from the negative side of the X and Y axis. So it's a way that you would describe the shapes of distributions, which is important because you're going to be asked this throughout the entire semester. So these are observational ways of describing the distribution. So there is a mathematical way of describing the distribution. So to find out whether the distribution is skewed, you can subtract the median from the mean. So always remember, that's the hardest part. Sometimes people get them mixed up. So think of the mean, okay, sorry, this is so sloppy, and then minus the median. So the mean's on top, okay, and that difference that you get is going to kind of confirm or disconfirm the observation of whether the data is skewed or normal. So if you subtract the median from the mean and you get 0 equal to 0, so I'm going to jump to this one, equal to 0, this third one, or very close to 0, and it depends upon the range of numbers. That suggests a normal distribution. That means that basically all the numbers pile up right in the middle, okay? But if you're subtracting the median from the mean and the difference is a positive number, it's greater than 0, that suggests that you should be seeing observationally that your distribution is positively skewed, meaning the tail is to the right. If you subtract the median from the mean and you get a negative number, that difference is less than 0, that should be confirming that you've seen a negative skew observationally. So is what the mathematical does is it confirms or disconfirms what you've already observed if you look at the histogram or the graph of the data. So you should always be first, number one, describing your data observationally, and then second, confirming or disconfirming what you saw observationally through math by taking the median from the mean. So it's two different ways that need to be kind of matched in this class. So when we report the mean, it's always when there's a normal distribution. If it's a symmetrical distribution that's unimodal, meaning one peak. So all of the majority of the data falls right at the 50th percentile, right in the center. And so if you have a perfectly symmetrical distribution, your mean, median, and mode should all be the same. And so with the mean, in a symmetrical distribution, it isn't influenced by outliers because there are no outliers. So it's right there in the middle, a perfect representation. And it's always used for interval and ratio data, so that continuous data. So data that is either interval or ratio scale data, because if you have data that is like categories, like male versus female, you're not going to have a frequency distribution that shows all the decimal places in between. So it has to be data that is either interval or ratio scale, so that it's meaningful as far as higher numbers mean a higher value. So the median is the best to report skewed distributions. So whenever data is skewed, either positively or negatively skewed, then you would report the median first and foremost. So the median is no longer influenced by the value of the numbers. It's just influenced by how many numbers fall on each side of it, the sample size or population size. So it's really good for using with data with outliers, specifically with the median. And then the mode, the one time the mode would be used as a standalone, like without reporting the mean or anything else, is if you have discrete data. So this is nominal scale data, but it could be ordinal too. So I'd say nominal or ordinal, so categorical data. So I think ordinal would also work with the mode. Now, you would report the mode if you're using a bimodal, or if there's a bimodal or multimodal distribution, so there's 2 or 3 peaks, you would report the modes, but you would back it up with a mean. So in that case, when there's continuous data, you would use it as the primary if there's 2 or more modes, but a secondary if or only a secondary if maybe for some reason the mode is something unusual. So a secondary for a bimodal and multimodal distribution should probably be the mean. That would be a secondary, but your primary measure of central tendency would be mode for any discrete data, for any data that is nominal or ordinal. So that's the primary measure of central tendency. So here I've given you a couple of examples, and these are the types of things that you're going to see on the exam, like a question like this: which measure of central tendency is appropriate? And so if you see this data set, here you have this bulk of data up here on the high end, and then you have this little bit of data here, which is and would be considered outliers. So in this case, your response should be a median. That would be the best measure of central tendency, because a mean would probably give you something around 5 if you were to calculate this, and that really doesn't represent the data because there's no one that scored 5. So you want to make sure that you would use the median as your primary measure of central tendency. So these are the types of questions you'll see on the exam. Here's another one. So we have POPs quiz scores, and if you notice, this isn't a perfectly symmetrical data set, but it's not terribly skewed. It isn't like it's horribly skewed. It's pretty close to being a symmetrical distribution. So I would say in this case, the best measure of central tendency would be mean, because it's continuous data. There's no gaps in between these bars, and there really isn't any major outliers. It isn't terribly skewed data, so the mean is the best representation. And in this case, we're just looking at preferences of beer. There's these 3 categories of brands, so Landshark versus Newcastle versus Red Stripe. You wouldn't say the mean because this isn't continuous data, and you wouldn't use the median because the median can't be used for categorical data. The best measure of central tendency is mode, because you have discrete variables that are either nominal or ordinal measurements. So that would be the example for when we would use a mode as the measure of central tendency. So hopefully that helps to clarify when we would use measures of central tendency and for what type of graphs or what types of data. So again, I'll kind of reiterate, with symmetrical distributions, the mean and median will have the same value. The mode will if it is a unimodal distribution with only one peak. So typically you'll see unimodal distributions where there's only one peak, and in that case, the mean, median, and mode are the same value. So that's one way to immediately notice whether their distribution is symmetrical, or what we call a normal bell-shaped curve. So on the exam, as well as on the labs, I'm going to be asking you to describe distributions, to describe a distribution. So some of the things you're going to look at is the mean, median, mode. And the last one, all of them had equal values, but what I'm really wanting you to do is be able to tell me observationally as well as mathematically. And the mathematical description should always follow your observational description, because as humans, our brains, if we see something like mathematically, our brains will kind of flip like the way that we observe things to match that already known information. The problem is if you've mixed up the mean and median and like which one you took from which, and you get the opposite, sometimes that will actually bias your observation. So you actually want to give the observation, the visual observation description first, and then follow it and confirm with the math. So if you'll notice, and I ask you this in labs and I ask you it on the exam, so to describe a distribution observationally and mathematically. So the first thing I do is I discuss observationally, the distribution appears to be a positive skew as the majority of the data piles on the low end with the tail to the right. And you could just say, because the tail is to the right side, you could just say that. That would be fine. Or the majority of the data falls on the low end. One or the other is just fine, but I provide both so that you can see what that looks like. And then I follow up that observation with the mathematical foundation. So the positive skew is confirmed mathematically, as the difference between the mean minus the median is positive. Now this seems like a small number, 0.5, that's a positive difference. But look at, we're only looking at scores between 0 and 9. So the range is really small. So a half a point is going to be very meaningful. So in this case, the median, if you'll notice, actually would be more than likely the best representation, because the majority of the people fall on this lower end. Now, it's not a terrible difference when we're deciding which median versus mean, but we do want to talk about, okay, it would be a positive skew. And I always throw in the little skier. As you can see, he's skiing down the gradual distribution. And so if this helps you, it's kind of a visual of how to tell whether something is skewed. If you are snow skiing, you want to ski down the gradual slope. You don't want to ski off of this cliff. So if you ski off of this cliff, that's to the negative side and you're going to die because it's a cliff. But if you ski down this gradual slope, you're skiing towards the positive numbers or towards the higher numbers. So it's a positive skew. You're skewing positive. So if you can kind of think ski and skew, it will help you. Which way would you want to ski? So in this opposite graph, we have all of the high numbers bulk up on this right end. And if you'll notice, our skier is going down. And if he kept skiing, he'd ski right down into the negative side of the x-axis. Hence the reason we call this a negative skew or negative ski. He's heading towards the negative side. So again, here's my response to if you're asked to describe the distribution observationally and mathematically. I talk about how it looks to be a negative skew because in this case the tail is to the right, or it should say to the left. Yeah, I don't know, ignore that. It should be to the left, right? This is the left side, this is the right side. I think there was a data entry error there. Yeah, because the majority of the data piles up on this high end. And then you would talk about whether it's confirmed or disconfirmed. So the negative skew is confirmed mathematically as the difference between the mean minus median is negative. If you look at here, it's a negative 0.5. So that confirms. So sometimes your math might contradict your observation. Doesn't mean your observation is wrong. You would just state that mathematically this was not confirmed, and maybe there might be some reasons. Maybe there's some bimodal distribution going on there or something, and so there's a lot of different reasons for maybe that not being confirmed. But is what I want to see is you both thinking logically through both of those, with the observational description first and followed up by the mathematical description. So at this point, we've wrapped up Chapter 3 and Measures of Central Tendency. This should help you on your exam, studying for your exam, as well as for answering the questions in your Lab 1. Please don't hesitate to send me an email or visit me during my virtual office hours if you have any questions or concerns. Thank you.